Hello all, I'm Jack with the Tutoring Center, and right now we are doing a video on log-log regression, also known as power regression. To start off, we are going to turn on our plots and enter the data into our list. We are going to speed this section up, but if you want more details on what is going on, check out our video on linear regressions. And here is a graph of our data. This data set does not look very linear, so next we are going to linearize our data. In order to do this, we're going to go back to our lists, and at the top of L3, we're going to enter in the natural log of L1. And at the top of L4, we're going to enter the natural log of L2. So now if we go back to stat plot, we can change our X list to L3 and our Y list to L4, and this will graph our linearized data. Now that's some linear looking data. Now we are going to get a regression line for our linearized data. To do this, we will have to change the X list to L3 and the Y list to L4 for the linreg function. We also still want to make sure that we store our equation in Y1. If you want to see a graph of our linearized data and the line of best fit, press zoom and then zoom stat. But now that we have found our regression line, let's jump over to the math window to find the power model for our original data set.
So with our calculators, we were able to just find this equation, which is going to be the line of best fit for what was the linearized data. But since we're trying to find the line of best fit to represent the original data we had, which was curved, we need to get this back into a better form to get that equation. So to get it into its original form, we remember that on our calculator, we made two new lists for the natural log of y and the natural log of x. So to account for that, I'm going to rewrite the x and y here as the natural log of y equals, all the numbers stay the same here, 4, 6. And then I'm going to rewrite x as a natural log of x. And then this number here is the same. LOL. So what we need to do now is get y all by itself so that it can look like a regular function. And so in order to get it by itself, we have to get it out of the natural log equation here, the function here. So to do that, we are going to exponentiate both sides. And by that, I mean that we're going to put both sides to the power for e, right? And remember that this entire side has to be in the exponent for e. And what we've learned before is that natural log is actually the inverse for the exponential equation. So this is actually all going to cancel out. And we're just going to get y here now. We can just go quickly through this part. Cool. So I rewrote our equation now with y here. And the next step is that we want to get it into the form y equals ax to the power. And what that is the general form for what a power function would look like. So to do that, we have this whole mess up here, but we can use the power rules that we have sitting over here to get x down to the bottom. And so what we first recognize is that we have this part plus, or in this case minus, this other number over here. So we can use this power rule where in the exponent we're looking at a plus b, and we get x to the a times x to the b. And so I'll rewrite that right here. Okay, I'll just keep doing it. I didn't have to do that. Just ignore me. Times e. And so now what we have is these two exponents being multiplied together. Over here, we have e to the negative 5.8888. And so since there are no variables in that, that is actually just going to turn into a number that we can calculate with our calculator and put back in at the end. So now we still have to get x out of the exponent. And what we have over here is this power rule, which has two things in the exponent being multiplied together, and we could rewrite it where there are two separate exponents going on. So what we're going to do is we're actually going to rewrite this term using that rule. This pen's freaking out. So I rewrote it like this, which looks like the power rule we have over here. But the reason for why I decided to take the natural log of x and bring it in to be the first exponent in the parentheses, I did that because what we did first was we exponentiated both sides so we could get y out of this natural log function. Here we can actually do the same thing, and these two are going to cancel out with each other. And so we'll just get that this term here just equals x. And x is still going to be to the power of 2.9746. And then lastly, we have this exponent over here that we found out was actually just the number 0.0028. And so I'm going to rewrite the general form y equals ax to the power here. And what we can see actually is that we have the y here. This a is actually going to be this number we have over here. And then we have x to an exponent. So what we can see was that we were able to get a new equation, which now we can plug into our calculator and use it to show a line of best fit for our original curved data. So to recap what we just did, we had this equation in the form of y equals mx plus b that was meant to represent our linearized data. But since our original problem had curved data, we wanted to get it back into a form in order to have a power curve which would represent that curved data. So what we did was we replaced both x and y here with the natural log of x and a natural log of y because that's what we did to linearize it. And then we put both sides up into exponents with e in order to get y all by itself so that we can get an equation. And what we did in order to get it to the final general form for a power function, we used power rules to slowly get x from being in the exponent all the way down to ground level so that it was able to reflect y equals ax to the power. And this was our final equation that we can now use to represent our curved data.
Now that we have found the power model for our data set, we need to find the error bounds for the model. To do this, we will first go to our lists and find the residuals for our linearized data. So go to the top of L5 and enter L4 minus Y1 of L3. Now that L5 contains the residuals, we can take the maximum of the absolute values of L5 to find the error of the model. Now, let's return to the math window to find our bounding functions.
So now that we have the error for our linearized data, we want to use it to find the bounding functions for our original power data. And to do that, we're going to first start off by finding the upper bounds, in which all we do is just add the error to the equation, right? And we'll do over here too. So the next step is just exactly what we did before, where we use all of our exponent rules to solve for y and get it alone. And to do that, just like last time, we started by exponentiating both sides. And then solve from there. So now we've gotten to this point again, where this exponent just becomes a number, which is 0.0030. And this e to the natural log of x cancels out again. We get x again. And this exponent stays the same. And that is our upper bounding function. To find the lower bound, all we'd have to do is subtract the error from our equation. And what we'd get from that is just 0.0026 now, with x to the same exponent. So basically, all that we just did now was that at the very beginning, we started with some data, which was curved and looked like it was a power function. So we were able to find a power model to represent that data. And all we did now was find an upper bound, which should just be a line just above it, and then a lower bound, which is a line below it. And what that does for us is gives us two curves that all of our data points will fall between. Thanks for watching. So to sum up what we just went through, like that was a traumatic experience. Okay.